All right, let's take a look at the second fundamental theorem of calculus. And you may be thinking, well, was there a first? Okay, well, sorta. We've been working with the FTC, the fundamental theorem of calculus, and as a quick review, it looks something like this. We were dealing with a definite integral. So we saw through some work that if I found the antiderivative of f prime and evaluated at the upper limit and subtracted the functional value at the lower limit, that was our FTC. We may have rearranged it. There's three possible ways to rearrange this, or two actually, for a total of three. Okay, that's the fundamental theorem of calculus, often called the first part. Right, so we have a second part as well. So that's what the topic of this video is about. Exploring what does the second fundamental theorem of calculus mean. All right, to help us do that, let's look at a description. It says if we have a function and it is continuous on an open interval I, that's I, containing a, then for every x in the interval, there's a lot of variables going on in here, so let me get some notation for you. Let's say that we're starting with an integral with a variable limit, a function defined by an integral, if you will. And if you remember from the other day, a is going to represent just a value, a numeric value. X is our variable, and because we have x up here, we would want to use some other variable down here. All right, so if f is a continuous on an open interval I, so this function, whatever graph it is continuous, okay, and it contains a, okay, a is there underneath the graph, above the graph. For every x in the interval, it's saying, okay, consider this that we did the other day. If I were to apply, maybe in a different color here, another operation to this, if you will, this notation. If I were to say find the derivative of this integral, I'm actually saying to perform inverse operations. I'm saying let's find an antiderivative only to turn around and find the derivative because of this derivative operator. Well, from your past experience, if you perform an operation and it's inverse operation, you end up with what you started with. It's the whole idea of if you take a number and you square it, only to turn around and square root it, you're back where you started. Inverse operations undo each other. So this notation and the integral notation right here are inverses of one another. And that's basically what the second fundamental theorem of calculus is saying. Okay, so what does this answer simplify? Well, if I were to integrate, I would lose the t. I replace every t with x, if you will, if you kind of remember from our previous work. My answer is f of x. So if you look at the integrand, okay, and you look at this answer, if I perform back-to-back inverse operations, I'm going to end up with the f function again, but just instead of this dummy variable, if you will, the variable of the limit that I have to plug in here. So this is actually the second, this whole thing right here is the second fundamental theorem of calculus. All right, let's do a little bit of work with our knowledge of this, this theorem. So what I'm going to kind of do is just kind of put this up here at the top. Now, I know I didn't have a worksheet for you on this, so if you just wanted to write this out here. All right. I want to go back and consider the example that we looked at the other day. You might recognize this function defined by this integral with a variable limit. Okay. All right, so what if today I said, okay, let's use the second fundamental theorem of calculus to find out an answer to this problem. I'm not really talking about what I did the other day. I'm saying, okay, second fundamental theorem means let's perform inverse operations. Well, I see this integral, then I'm going to have to perform differentiation. All right, so the long way would have us do this. The long way would have us say, okay, I've got two operations. Let me perform this inside integration first, get an answer, and then differentiate it. So I guess that's what I'm going to do here. So now I'm focused on this integral right here. Well, I could go through all the work, but if I remember correctly from the other day, when I find an antiderivative and evaluate the function that resulted, defined by that integral, sine x minus 1. So I'm just replacing the brackets with the answer to the integral. Okay, well, am I done with this problem? Absolutely not. The next step is to differentiate each of the terms. So I see my next move needs to be differentiate sine. I get cosine. Differentiating 1, the constant, gives 0. So if you think about what we have here, if I undo the integration by differentiation, okay, study what's going on here and look at your final answer. Okay, I end up with the cosine function again, but just with a change of variables to x. Okay, might be thinking, all right, got it. A little bit more to it. Let's continue. All right, let's look at another example here. What happens when we kind of work with the variable limit and change it up a little bit? It's not a basic x. It's something more complicated and complex. It's the variable expression 7x. Okay, well, is my answer still going to be cosine when I differentiate? Okay, so let me get back to, what if I'm presented with this problem? What if this problem is given to me right here all together and I'm asked to find the answer? You quickly notice we have inverse operations. Is my answer cosine x? I don't know. Let's go through all the work to see if my answer is like this previous problem, cosine x, when I make a change to the variable limit. So we are going to have to go through all the work here. So let's drag over d over dx. That'll be the last operation I perform. Okay, and my brackets are just going to be the representation of my doing work here. Okay, so sine is the antiderivative evaluated from pi over 2 to 7x. Okay. All right, so I'm going to keep the d over dx. All right, so now I'm on the inside here. I need to perform those calculations. So I've got the sine of 7x. And then I have minus the sine at pi over 2. All right, I'm going to drag this all the way over here. All right, I still have the derivative operator I need to perform. Let me do a little cleanup on the inside of that bracket. It's too much trouble to change colors. All right, sine of 7x minus sine of pi over 2 is what, 1? Okay, so already you can observe that this expression right here is different than this expression right here, this function defined by that integral. All right, well, I'm getting closer. Let me continue. Let me finish this problem. All right, in this case now, I still need to perform differentiation. I've done the integration. Now it's time for the differentiation. The derivative of sine 7x. Well, it's a composite function. We'll be using the chain rule. Derivative of sine is cosine. Leave 7x alone. But we also have to multiply by the derivative of the 7x. Okay, I'll come back and clean that up in a minute. Let me move on. What's the derivative of a constant? Well, that's 0. So back to my cleanup here. I see that this derivative is 7, so I know many of you guys would be able to write this down real quickly. Okay, we get 7 cosine 7x. Okay, that seems like a lot of work to integrate only to turn around and differentiate. Okay, where we want to go with this, with the second fundamental theorem, is we kind of want to look for a shortcut. So perhaps let's just take a look back at this original problem. and the final answer, and try and avoid doing all this work. Okay, what can we see as possible shortcuts that would allow us to get a quick answer if we know we're differentiating and integrating? We're undoing something. Well, I see that my answer has also the same function, cosine, but I notice that this isn't just x, it's 7x. So I'm seeing that maybe I replace the variable t with the variable limit. Well, that seems to work. That seems like a plausible shortcut, and that's what we're doing through this whole process here. We're replacing the t in with the 7x. Okay, keep the trig function, the function itself, replace the variable limit in for the variable in the integrand. Got it. But where'd the 7 come from? Well, if you remember, the 7 came from the chain rule here. Well, the 7 came from the derivative of 7x. 7 came from differentiating the variable limit. The derivative of 7x is 7, so I'm going to put that in the front here. That's my answer. It appears that I could perhaps avoid going through all this work if I know I'm performing inverse back-to-back operations, okay, by taking 2 steps. It appears that I'm finding the derivative of a variable limit, 7, here it is, and then replacing in the integrand, okay, that variable with the variable limit and getting cosine 7x. All right, let's go back to the previous problem and see if that also would work here. This is kind of a special case. All right, here we go. Here's the problem. Can we avoid this work and get right to the final answer? All right, I've identified back-to-back inverse operations. 2 steps. Derivative of the variable limit. Derivative of x with respect to x is 1. Sure, there's an understood 1 there. Replace the variable limit in for the variable in the integrand, rewriting it, cosine x. Seems to work. I think at this point it would probably be a good idea to do one more problem to kind of verify that our shortcut will work for every situation. All right, let's look at another example. Okay, thinking that we're presented with this problem, we are going to go ahead and go through the long process of integration and then differentiation. Okay, but let's think about the shortcut we saw previous. Can we kind of make a conjecture as to what we think the answer might be based on the patterns I saw? And then going through this problem the long way, verifying that that works? All right, back-to-back inverse operations. First thing I saw was, I'm just guessing. I'm thinking that my answer, questioning, okay, maybe the derivative of the variable limit, because that's just 0 anyway. Derivative of 3x squared is 6x. Looking into the integrand, keeping everything the same, any part of the function the same, except for changing the variable by inserting, everywhere I see a variable here, the variable limit. So I'm thinking my answer is going to be 6x cosine 3x squared. That'd be nice if I could perform those 2 steps and come up with an answer without having to go through the whole integration differentiation process. All right, back to the problem. Let's go ahead and do the integration first, which means I'm going to keep the derivative operator along for the ride. Now, all my examples have been dealing with cosine just because it's easy to work with, but it doesn't matter what function is here in the integrand and I integrate. It just works easier if I have a nice function to work with. So antiderivative is sine t, evaluate 3x squared. So inside here is our fundamental theorem of calculus, if you will. Okay. All right, let's continue. D over dx, sine of 3x squared minus sine of 3. Okay, coming down here. Ready for differentiation. I performed all the integration I can do. All right, let's look at this first term here that I'm differentiating that resulted from my replacing 3x squared in here for t. Well, it's a composite function. It requires the chain rule. Derivative of sine, so this is equal to, because now I'm in this next step, cosine, leave the inside function alone, times the derivative with respect to x of the 3x squared. I'll come back and clean this up later. Okay, now what's the derivative of this constant number? Well, it's going to be 0. Okay, so I get a constant here, and derivative is 0, so actually I'm needing to finish this up now. This action requires my finding 6x as the derivative, and probably putting it in front of cosine 3x squared. Think about what our conjecture was up here. It is exactly the same. So perhaps if I identify that I'm asked to perform two inverse back-to-back operations with integration and differentiation, the fundamental theorem of calculus part 2, the second part, okay, tells us that we can perform this shortcut. Differentiate the variable limit, multiplying it by the replacement of the function here, integrand, with that variable limit. So I'd like to look at one more with you real quickly. We're going to perform it the long way, but we're first going to see if we can assume what the answer is or guess what the answer is. Only because I want to mix it up a little bit and use another variable besides t in the integrand and not cosine. And that's an exponent of 2 up there. Okay, thinking about the pattern that we developed here, let's see if we can kind of make a guess as to what we think the answer is going to be. We are doing inverse back-to-back operations. First step, find the derivative of the variable limit. So I'm going to come over and go, I think the answer is going to be 4x, the derivative first, times, everywhere I see a variable in the integrand, replace that variable with the variable limit. So this would look like 10 over, now v gets replaced with 2x squared, and then I have to square that in the denominator. So v is the 2x squared and then square it. Okay, so let me clean this up and see if maybe this is what I'm going to get by doing it the long way, and then I'll feel comfortable using the shortcut. So I have 4x over 1 times 10 over, this squared would be what, 4x to the 4th? Okay, cleaning this up, 4 and 4 and x, and this is a third. So it appears that my answer is going to be 10 over x cubed, or 10x to the negative 3, whichever. Okay, I'm thinking that should be the answer if I do the shortcut with the 2 correct steps, but let's go ahead and work through this the long way. Hopefully I can get that done quickly here. Okay. All right. Hold on to the derivative operator. Oh no. Okay. Rewriting 10 v to the negative 2 dv. All right, so let's go ahead and continue with this problem. I think I'm going to move down here and continue it. The antiderivative, this looks similar to something we did the other day, would be 10v to the negative 1 divided by negative 1, which makes this negative 10, evaluated from 5 to 2x squared. All right, so remember, we're doing this long way, seeing if we're going to get the same shortcut answer right here, that's a valid approach. I could pull the negative 10 out and put it in front as a constant multiplier. I think I'll just work with it the way it is. It's negative 10, and it's going to be 2x squared in the denominator if you wanted to pull v to the 1 in the bottom. So that would be 2x squared. It might have been better if I left it up here, perhaps so, because I'm about to differentiate. Should have done that. Minus a negative 10 over, looks like v's down here, a 5. Well, I definitely have another opportunity to rewrite it, get it ready for differentiation when I clean it up. And that's what I'll do. I should have left it that way, but that's okay. Negative 10. Oh, well, you know what I could do? I could clean this up and make this negative 5. How about that? Negative 5, x to the negative 2. And then this would be what? Plus 2? All right, now I'm ready for differentiation. Hopefully all will work out. It should. I think I have enough space here. All right, the derivative here would be positive 10 x to the negative 3. The derivative of a constant is 0. Checking, yes, it does work. Yes, I feel comfortable, confident that I can take the two-step shortcut process when I know I'm asked to integrate and differentiate. That would be the second fundamental theorem of calculus. So in the next video, I just have some extra practice problems for us. Now, I'll attach the handout for these extra practice problems if you don't want to write them down. And you can print it off from Sophia, or they're not too bad. You can just actually write them down. I have a total of 8 examples. So if you wanted to print off the worksheet, I'll attach, fine. And if not, just in your own handwriting.